Hey everyone, welcome to this video. In this video, we're going to be taking a deep dive into the leap exercise in Exercism, looking at how different people solve it in some different languages, in some different ways, and some different methodologies. I've got Erik with me. Hi, Erik.
Hi, everybody.
So Erik's chosen 10 different solutions that we're going to go through and look at. They start off with a couple of sort of cheaty ones, I guess. Then we're going to look at a couple of the normal sort of standard solutions that people do. We're going to then dig into some slightly more interesting ways with some slightly maybe more complex languages or languages that you won't use so much. We're going to end up looking at Prolog. We're going to end up looking at assembly. And then we've got one solution right at the end, which is just a bit OTT and a bit weird. So yeah, let's dig in. This is the first one we've got on screen now, which is the Cheaty version, Erik. So we always discourage people from doing this one.
Yeah, true. So if you do this in C#, you actually, in the README, there will be a line, don't use the built-in function method. But people will still do it because, well, it's easy. And of course, this makes total sense, of course, because virtually every single framework out there will have a built-in function to determine whether or not it is a leap year. Because dealing with leap years is important. You don't want to, I don't know, send an invoice in February that is supposed to be sent later, etc. But this is the default way. It's not wrong. It's not in the spirit of the exercise, I would argue, but it's still valid. So what I did is because the .NET framework is open source, I looked for how it was actually implemented in the framework itself. And if you do that, you'll actually find that there is no such thing as a leap year, but instead there is a leap year within a calendar. So you have the Julian calendar, which is an old calendar, I think it's Julius Caesar, and there was just modulo 4, so it was a very simple one. And later on we had the Gregorian calendar, and then it became a bit more nuanced, where it had to be modulo 4, but only if it wasn't a multiple of 100, unless it was a multiple of 400. But there are also other calendars, like the Hebrew calendar has its own leap year determination system. There's the Ricci calendar. I'm butchering that, but there's a different calendar too. And they all have different logic. So just saying that whether or not something is a leap year is, in Western minds, is based on the Gregorian calendar. But on different places in this world, there will be a different thing, how they determine a leap year.
The idea of, looking at this, I don't know how to spell Hijri, I think Hijri.
Yeah, sorry.
Which is year times 11 plus 14, modulo 30 is less than 11, is that's quite a funky way of doing it. This, I'm just looking on GitHub as well. There's like 2 pages of these things. It's a Thai Buddhist calendar. Really fascinating. Nice find. And how do they actually do it for the Gregorian calendar? I guess. Okay. So it's
get to
solution
that in
we're going to see in a couple of minutes anyway.
It's
Nice.
Probably the solution that most people will actually write when they do this exercise. So we'll get to that in, I think, 2 solutions. So
yeah. Okay, fun. So okay, nice. So that's our first solution, which is purely cheating. There are some languages, I know Crystal does it, I think a couple do, where actually if you use the inbuilt function in the language, it will actually just tell you that's not allowed, and it won't pass the tests. So that's quite a nice one to do. Next up, we have this solution you've highlighted by VoxEco in Python. But this is, do you want to talk us through what they're doing here, Erik?
So, the defining feature of a leap year in our calendar, and which is the one that the exercise uses, is that there are 29 days in February, but only for leap years. So if you are at the date the 28th of February in a given year, and you try to move to the next day, you can then just check whether or not that the number of the day is 29. If so, it must be a leap year, because you're then at the 29th of February. And if it isn't, you'll be at the 1st of March. So this is a very simple way of, or simple-ish way of exploiting the fact that a leap year means that there is a February 29th.
I really like this, actually. I think it's quite... I know it's sort of, again, maybe not in the spirit of the exercise in some ways, but I actually think it's quite a cool solution. I'd be interested from a benchmarking perspective as well to know how this performs. I guess it's a bit slower, probably, because you haven't... It's probably using the same formula underneath to work out what the +1 is, whether that goes to 29 or not. So, but yeah, I quite like it. You're not a fan, though, are you?
I'm not a fan. If I were to cheat, I would use the first version because that would hold for all the calendars. This is just the Gregorian one. So.
Yeah. Okay. That's fair. Well, let's look at an actual passing real solution. And this one, I think, in JavaScript, this is Osinski's. I don't know how I'm supposed to pronounce that. OS in Sky is another potential way. This is their version, which this one is the same as what is in the .NET framework for the Gregorian.
I think it's actually literally the same thing, except for the fair fact that we use triple equal signs here, because that's not valid C#. But if you squint a little bit, it's the exact same logic. So if you do the leap exercise, the instructions will tell you that to determine whether or not a year is a leap year, it has to be a multiple of 4. So that's the first condition, a year modulo 4. For those that don't know modulo is the remainder. So it's what you get after dividing whole numbers. So if you have, 6, and you try to divide it by 4, you can divide 1 4, and you are left with 2. So if you do that with 7, you're left with 3. If you do that with 10, you get 2 4s, and you are left with 2 again. So 10 modulo 4 is the same as 6 modulo 4. And we don't need to go into more detail. But that's the whole key to determine whether or not a number is a multiple. So the first bit is checking if it's a multiple of 4. But that's not enough. It was enough in the Julian calendar, but not in the Gregorian one. So the second part is it must not be a multiple of 100. So 1900 would not fit unless it's a multiple of 400. So 2000 would fit, which is a multiple of 100, but it's also a multiple of 400. So, and then there are more interesting things about this, even though it looks very, very simple. You can see the parentheses here. They're actually not needed because of the way that the operator parentheses, they are needed here because of the way of operator precedence. So if you would omit them, you would get the wrong result. So I can't really draw here, but if you remove the parentheses in your mind and you put them around year, around the first year percentage 4, and then the year percentage 100 not equal to null, that will be the first expression, because the ampersand, which is a logical and, has higher precedence, which means that it will be executed first than the or. So you could then read it as the year must be a multiple of 4, and it must not be a multiple of 100, or it must be a multiple of 400. So that will work unless you swap out the order. So ordering is really important. And we don't really want to... most languages use sort of the same operator precedence rules, especially for Boolean logic. But it's very common to have it be made explicit via the parentheses. But do be careful that the ampersand has a higher operator precedence than the or. So if you get weird errors, try and see if you can work around them with the parentheses.
Yeah, and some languages are different in their precedences, as you said.
Yeah.
And so it's definitely it's quite useful exercise to do actually in lots of languages, just to understand that and to just sort of sanity check your knowledge of the precedences in those languages. There's another thing as well, which doesn't really affect this so much, but the modulo operator, the percentage here, is different. In some languages, it's a modulo operator, and in some languages, it's a remainder operator. And when I was recording some of the videos for the Go track recently, it was interesting comparing Go and JavaScript and how, with negative numbers, you'll get different results in those two languages using the percentage operator as well. So there's a lot of little gotchas and catches and things in here. But fundamentally, this is a pretty straightforward line of code. It's pretty...
you can see the instructions here, basically. So
yeah, exactly. So jumping on to the next solution, because this is, I guess, very similar. This is Hop's solution in C. But yeah, it looks very similar at first glance, Erik. Do you want to talk us through it?
It's similar. There are a couple of minor differences. If you so the previous version had 3 different conditions that could be executed. If it was a multiple of 4 and it was a multiple of 100, then it needed to also check whether or not it was a multiple of 400. So that would be 3 conditions checked. So 3 checks. But this version would at most do 2 checks. So you could argue, well, this must be more efficient. But actually, is it? Because the very first condition is to check whether or not a year is a multiple of 100. So with very basic logic, there's of every 100 numbers, there's just one that is a multiple of 100. So this will be a useless check for 99% of the numbers. So the very first check is not as useful as the other check, because the multiple of 4 is like 75% of numbers will not match. So it's at least a lot better there. But you do have just 2 checks. So the order must be different here too. So we previously started with year percentage 4 equals 0, but now you have to swap them around a little bit, because otherwise the logic doesn't work. So there is no not here. So that's different, but it's actually, of course, the very same equation. It's just listed a bit differently. And well, whether or not you like that, you can argue. Whether or not performance should actually be an issue with these very simple things is also another thing, because it will be incredibly fast regardless of the language. So I don't know. If you're into micro optimization, you might look into that.
Yeah, it's really interesting to think about how it could be. Yeah, you know immediately that 99% of numbers are going to fail that first check. Like that wasn't intuitive to me as soon as I looked at the code. So yeah, thinking about those optimizations, it's quite fascinating actually to think about. Which of the 2 solutions do you prefer out of those 2, Erik?
I think I like the first one a little bit better, because it's more easily tied to the instructions. So I think it reads a little bit better. I've used ternary operators a lot, but I'm always sort of in a love-hate relationship with them, because they are really concise. But I'm not always sure that they're the best way to have readable code, because they're very subtle. But oh well. Personal.
I used a double ternary earlier, where sort of in the same line you've got A question mark, B question mark, C colon D, and once it gets to that point, especially because you don't need brackets in there as well because of the precedent, it can start to get quite unreadable and quite unwieldy quite quickly.
I think that's where you want to have
sort of where I
think, but
draw the line.
Yeah,
exactly. And pattern matching is something that we're going to look at in a minute for this as well.
So there are the very same solution I looked at in Kotlin, but they don't have the ternary operator. Instead, they have if expressions. So this would be an if, then if. So that version I actually I didn't include it here because I think most people will be more familiar with this one. But if your language has if expressions instead of ternary operators, it suddenly becomes more readable again, I think. Although I would still prefer just the Boolean expression that we had before.
Okay, let's move on to Clojure. This is your solution you've chosen here for Clojure.
I'm totally unbiased. I just tried to find a solution. I will admit there's another one of mine later on, but I didn't spent hours looking for the one that fit.
It's quicker not to have to search for everyone else if you know you're happy to highlight your own. So I guess just distinctively less people probably are instantly familiar with Clojure. This is pretty readable Clojure. But do you want to just talk just sort of very quickly, top to bottom, what's happening here in this code, Erik?
Forget about the first line. That's just a namespace thingy. So define is defining a function. So the first function that I define here is also why I wanted to show this solution too, is that this is also happening in a lot of other languages where people have a helper method that sort of wraps that whole modulo bit. So you could have, in C# too, you could have a method that takes two numbers and determines whether or not the first one is a multiple of the second one. So that's just what this does. It's just a simple helper function that says, rem is obviously the remainder. So the way that you call functions in a Lisp-like language is that you put them between parentheses, and the first thing is what you are calling. So in this case, we're calling the rem function with two arguments, x and y. And then we're passing that result to the function 0, which returns true if the value is 0, and it will return false if not. So this is the same thing that we did with the modulo code, where we checked if modulo a number was equal to 0, only this is written in a Lisp-like version. So don't be bothered by the parentheses. It's just a different way of writing things. It's not actually doing anything majorly different here. What is different here is I mentioned that we had operator precedence where the and has a higher precedence than the or, but you don't have that in Lisp languages. And that's because there is no such thing as the operator precedence, and you have to be explicit about it anyway. So Clojure doesn't need it. We had the option in the JavaScript version to omit the parentheses, and then it will still work because of the way that it is evaluated. But in Clojure and Lisp, you have to be explicit about it because you don't. You have to call the. So you can see that we're calling and here, and the first argument is divisible by 4, and then the second argument is sort of like grouped in parentheses, which is the or, and the or itself has two arguments. So the not divisible by 100 and the divisible by 400. So there is never any doubt what the operator precedence is because there is an operator precedence. You determine by the order of the the calls, so the parentheses, so the parenthesized groups of code, what the evaluation order is. So you are fully in control. There can't be any surprise.
And the nesting makes that really nice to read as well with the indentation. So you can very clearly sort of see the patterns of that.
That's where I spend a lot of time arguing with myself what is the best way to indent this. So because there are a lot of opinions, I could easily, you could put this on a single line, but I don't think that will be as readable. Mm-hmm. But
no, I think that's I think it's really clear at a glance as to what's going on here.
There was another thing that I would like. Oh, sorry.
Yeah, go. I was just going to say, I feel like it's often the case with Lisp-like languages, or Lispy languages. Once you become a bit more familiar with the brackets and with the the structuring of functions and things, actually they become incredibly readable. And I think a lot of people at first, not being familiar with this, would think it's very confusing. But you only need to actually look at a small amount for it to become pretty readable pretty quickly, I think.
You'll get used to it real quick. And otherwise, you can watch our Summer of S expressions video.
Yes, that's true.
So small plug. Now, the other thing that I wanted to mention was that I defined the divisible by function outside of the leap year function. But in many functional languages and in other languages too, it is very common to have nested functions. So I could move that within the leap year function here. And that means that within that divisible function, that second parameter, that y, that first one, that x, which is always the year, I wouldn't need to pass that because I have access to it because I'm defining it within the function. So all functions defined within an outer function have access to its parameters. So it means that I could write and divisible by 4. divisible by 100. So I don't need to pass in the year because the year is always there in the scope. I tried to see if that would make sense trying to explain this in code, but I thought this version was a bit more readable. And of course, this has the advantage that theoretically speaking, you could reuse that divisible by logic. Whereas if you make it a nested function, you couldn't because it's local to that function.
I guess you could start to do things like currying and things at this point as well. If you define one inside. Cool. Okay. Should we move on?
Yeah.
So let's next go to Rust. So in Rust, well, again, I guess Rust is less familiar with people, although this does feel pretty readable again. But do you want to just talk us through what's happening here, Erik?
Yeah. Again, it's just a function definition returning a bool. But the key thing here is that we're now using pattern matching. So pattern matching is a way you could think of as like if statements on steroids. You can't just match on Boolean condition, but you can also match on the shape of things. If you've never heard of tuples, they're basically like a collection of values, usually unnamed values, and each value can have a different type, although in this case they don't. But if you see the match and then you have parentheses, so those parentheses indicate this is a tuple or a tuple. I don't know what I always say tuple, and I've heard people say tuple, but
I say tuple.
Okay, whatever. It's tuple, tuple. I'll just go with what I have been using all along. But basically, we are constructing a value, a tuple, a tuple with 3 values. So the value of year with the remainder of 4, year remainder of 100, and year remainder of 400. So that's a tuple with 3 values, and then we can see we can look at its pattern. So line 3 has the parenthesis opening underscore, which means that we are not interested in that value. We are not interested in the second value, but when the third value is equal to 1, so that's the year percentage 400, we return true. So think for yourself, why is that true then? Well, it's easy because the condition was it has to be a multiple of 4, and 400 is a multiple of 4, so that holds. It must not be a multiple of 100 unless it's a multiple of 400. And well, it is a multiple of 400, so we don't ever have to check the other 2 conditions here. We say we don't have to check them, but they are executed. So this isn't as efficient. So we're doing 3 conditions here. But the pattern is then moving to the next one is if we move to line 4, that means we know that it is not a multiple of 400. Otherwise, the line above will match. They will match from top to bottom. And in this case, if it's a multiple of 100, then it's not a leap year. Then we do the same thing on the next line for whether or not it's a multiple of 4. So that means there is a 0 in the first place of the tuple, and then we return true. And otherwise, which is the underscore on the line 6, will return false. So this is actually a quite functional way. Well, Rust is a systems language mostly, but it has actually a lot of functional things in the language. So you wouldn't blink if you were an F# or a Haskell developer. You would immediately recognize the thing that's being done here.
It's really nice. I think the one thing that would be even nicer maybe would be to combine this with what we just saw in Clojure, where you have a divisible by function. So rather than pattern matching on the zeros, you could be pattern matching on trues in those 3 things. So if each of the year remainder of 4 was actually just a divisible by 4, and that would make it even more readable. Yeah. But it's a really nice solution. This is Eco's solution, EYKO in Rust. And I just think, it takes a little bit of getting your head around a little bit, sort of with all that Boolean logic, you're holding in your head knowing that the one above was false, so therefore those 2. But once you get through that, it's pretty elegant. I like it. Are you a fan of this?
I am a fan of pattern matching. Whether or not, I think the problem here is that I don't see, if I just look at these cases, so these patterns, I have to constantly go up to see what is the order again of what am I actually looking at? What is the third argument of the pattern? So there's a bit of a disconnect between the pattern and the input, because, well, it's just A0, and A0 well, could be a ton of things. It could be, I don't know, year -2 or whatever. So that's the main problem I have here. But there's so little code that it probably doesn't really matter.
Yeah. I mean, I think one of the things you commented on with some of the first solutions was that, especially the Boolean logic one, is that the algorithm is really readable through code. You can understand the instructions, understand what a Gregorian leap year is just by reading it. I think at this point we've moved away from that, and it's now harder to decipher the algorithm. You could work it out, but it doesn't shout out at you, I think. Okay, cool. Let's move on to Elixir. So Elixir, I guess using guards here. Do you want to talk us through this one?
Yeah, so this is actually also a form of pattern matching, only Elixir does support pattern matching within a method, but it also supports pattern matching at the method definition level. So what you see here is, if you're not familiar with Elixir, this will look quite weird, because you'll have 3 definitions of a function, of a method with the same name. So we see leap year, question mark, 3 times. But the thing that is different is that the first 2 have a guard clause. So you might notice that it has when, and that when means there is a condition, and only if that condition holds will we execute the body of the function. So the first leap year says, execute this when the remainder of the year 400, when the remainder of division by 400 is equal to 0. So about the same logic that we had before. Then we do the body, and in this case, Elixir has a shorthand format to not have a do end block. But if you have a very short statement, you can just do comma do colon and then the return value. That's what they're using here, and that makes absolute total sense. So in this case, return true, and that's the end. None of the other leap year methods will be executed, because this, again, matches from top to bottom. So if the guard clause doesn't match, it will move to the second one, try to match that, which in this case is whether or not it's divisible by 100. And if it is, we'll return false. And in the other case, which is like the catch-all or the underscore that we had previously in Rust, we'll just return the result of the remainder equal for being equal to 0. So it's a different way of doing pattern matching, but at the method level, and it's quite a fun thing to work with.
Yeah, it's really cool. I'm a big fan of Elixir, and these guard clauses on methods or on functions, I guess, they're such an interesting way of writing code and thinking about code. It's really nice to not have all of these nested conditionals and things sitting within functions, or having to have functions that are calling other functions to do that. It does make, I think, the code just feel a lot more elegant and readable. So yeah, cool. Really interesting solution. Do you prefer this or the Rust one? Because they're sort of similar, I guess.
I prefer this one because it's I think it's easier to read, because the remainder and the check are at the same in the same line. So previously you had the remainder execution at where we had the match, but then you had the case a little bit further along. So these are now grouped together. I like that better. It also helps that we have a document comment here, so you can see the rules that further reintroduces. And they could actually do more cool stuff here, where you can add tests within the comments. And I always really like that you have executable tests within your comments.
Yeah. Elixir is a cool language. If you've not tried Elixir, you should do functional February videos on the website. Do we have a brief introduction to Elixir as well, Erik?
I think we do.
If you did that.
Yeah.
Okay, cool. So there's an introduction video from Erik on that. There's also a video of me introducing Jose Valium, who created Elixir. So yeah, lots of Elixir content on the YouTube channel, so go and check that out. Credit to M Stranger for this solution. Okay, let's take a step further. We're moving into Prolog. Erik, talk us through some Prolog.
It's one of our favorite languages. So so Prolog is absolutely different. I think it was in Mind Melting May. What was it? I don't even know what we named
Mind
it.
Shifting May, I think.
Mind Shifting May.
Mind Shifting May.
But it could have been Mind Melting May if it's Prolog.
We should have done Mind Melting. Yeah, I feel we got that wrong.
Yeah,
Mind Shifting May anyway.
So Prolog is sort of different in that it works on relations. So you're saying if this hold, then that holds, etc., which is sort of similar to Boolean logic, but it's also different. But in this case, it's not that bad. So we see we have the same thing where we're checking for the remainder being equal to 0 or being unequal to 0. Although you're probably not used to unequal being equals / equals. So there are good reasons for that, but which we won't go into. But you're probably also not used to being equals colon equals. So Prolog has funky operators, but that's because the default equals is doing something else. Go check the Prolog introduction video if you're interested in that. But we're doing the same logic, but there are a couple of things that are different here, except for the weirdness of the operators. So there's a comma within the third line, and the comma is basically saying and. So the third line is saying it must be the remainder of 4 must be equal to 0, and the remainder of 100 must not be equal to 0. So that's the comma. Then there's also a semicolon, which is the or in Prolog. And there is a thing that's an exclamation mark. And that's the most interesting bit here. So in Prolog, there's a feature called, let me get the right name, choice points. So choice points are, Prolog is doing a search of the search space. So it will try to find any solutions that match a certain relationship. So in this case, if a year modulo 400 is true, then we know that it's a leap year and we can stop execution. But by default, Prolog would start looking at the other rules. So with the exclamation mark, we're basically saying, hey, Prolog, at this point, we know that this is the end of your search. Just stop searching, immediately return, this is true. You don't have to continue. But if you wouldn't, Prolog would happily try to find any other rules that match. So any other values that match the other rules. So the choice point thing is somewhat weird at first, but it's really, really powerful. Even though this isn't the best way, the most natural way to show its usefulness here. But just for now, remember that it's just like an early return, basically.
Yeah, I'm looking forward to when we get to highlight some really cool Prolog solutions later on in these videos. But yeah, this is a nice basic one, again, just to show how Boolean logic is done in a totally different sort of paradigm here.
And you also see there's very little syntax being used. There's not a lot of unnecessary stuff here. So we don't have the curly braces. We don't have a lot of that. So I think that also makes this quite readable.
Yeah. As soon as you sort of understand the operators, obviously they're different. You're not having an ampersand, you're having a comma instead. Once you get those things in your mind, again, it becomes really readable. There's just that sort of small learning adoption curve to get that into your mind at the first thing. Cool. So that was divisible-by, I'm guessing is how you pronounce that. Their solution in Prolog. So next we're moving on to something that I think will be much less readable for most people at first glance, which is your solution. No offense.
Sorry.
Your solution, but in MIPS assembly. Again, do you want to just talk us through this one, Erik? It's not as bad as it looks, everyone.
No, definitely not. So MIPS assembly, it's an assembly language, so it's very low level. The very first line is just saying that we are, it's like an export that you often see. It's like letting Kotlin code know what is there that you can call from this file, basically. And then is leap year. So that's the thing that we are trying to run. And then we get to the actual meat of the problem. So how assembly code works in MIPS assembly is that you work with registers. You can see them as like variables. So they can have values and they can you can add things, but it will always be doing something with a value in a register. So let me explain to you. So when this method is this is the function nor a method. When this code is being called, there is a value in $A0. So if you look at line 4, that you see rem, and rem is probably something that you will recognize. It's the remainder. There were other languages that use the same thing. But let me explain what the arguments are. So there are 3 arguments to rem. You'll recognize the 4. That's of course the value that we. That's is it divisible by 4 thingy. $A0 is the value that we are checking for the remainder again. So that's our year basically. So you just have to assume that the value in $A0 is provided by the test with the right year. So that is all done for you. You don't have to do anything. And then what T0 is, T is like a temporary value. We're saying the result of the remainder check is stored in T0. So if the number A0 was a multiple of 4, there will be a 0 in T0. But if there isn't a 0 in that T0, so it's not a multiple of 4, then we know that it isn't a leap year. So the BNEZ stands for branch if not equal to 0. And it takes 2 arguments. So the first one is the value to check for whether or not it's not equal to 0. And that's T0, because that's the register that we just put the remainder in. And the second value is the label where we need to jump to. So you have to scroll a little bit down, scroll to __ false. And that's the code that then gets executed. There's a single line there, which is the instruction li, which is the instruction that you use to load a value in a register, an immediate value. So we say here that in the value 0, the second argument, must be put in the register $V0. And the convention is that $V0 contains the return value of the function. And then it will move to the next line. So we skip over the label thingy, and it says JR to $RA, and that's basically return to the caller. So you don't need to know that. So that was the part that we took. But if we scroll back up, so BNEZ only jumps when the value was not equal to 0. What happens when it is equal to 0? Well, then it just moves to the next instruction. And the next instruction is checking for the remainder of 400. We store the result in the T0 register. We could have used a different register, but as we are we don't want to keep that previous value anyways, we could just override it with a new value. So after that line 6 instruction being executed, the remainder of division by 400 will be in T0. If that is equal to 0, so that's BEQ0, branch if equal to 0, then we jump to the true label, because we know that then it is a leap year. And we do something similar to what we did before, but now we're loading the value 1 in the return address, and the 1 is interpreted as true, whereas the 0 previously was interpreted as false. And then we do jump to return, and we need that because otherwise we would go to the second line, and we will put the second line, the next line. So the next instruction is load 0, so we would override our true value with false. So we need to skip that. And that's why we do the J, which stands for jump, and we jump to the return label, and that's the end of the function. Well, then we go back. So you can see here why assembly is a lot different. There's a lot of jumping around. We do the remainder of 100, and we do branch equal to 0 check. And if it is 0, we jump, because then it's a multiple of 100. It's not true. If it isn't, we just go to the next instruction, which is the true bit, and then we jump to the return. So there's a lot of jumping involved. But the key part is here that you are determining the remainder, and you store it in registers, and then you compare values in registers, and you jump to labels, so certain parts of the code. So you can maybe start appreciating how much the other languages are doing for you, because they are doing stuff like this. If they are targeting MIPS, it might actually look very much like this. If they're targeting another, like an x86 64 CPU, it will look different, but still akin to what we have here. So I think it's a very good thing to start trying to write MIPS assembly or another assembly language, just to get a better idea of what the other languages are actually doing for you.
And I think, yeah, one of the things that I like about this, looking at this for Leap in particular, is you can see, very clearly what, I don't know, we looked at, was it JavaScript, I think the first one we did, which probably isn't compiling to MIPS assembly, but if it was compiling down, you could see, very clearly what that higher level line of code is actually being compiled down into these, I don't know how many lines of code we've got, 16 lines of code or whatever. It's really interesting to see that direct parallel, because I think often with exercises or more complex code, it can be hard to see the correlation between the resulting assembly and the code you've written, because it's so abstracted.
Yeah.
Whereas because we're using sort of basic Boolean logic here, you can see that comparison much more closely.
Yeah. So I like this.
Yeah, it's a nice solution. It's neat. Okay, so final solution we're looking at, and we're throwing this one in just because it's crazy. I think probably let's not walk through the whole of this, because there's quite a lot of code in here, but maybe just you can give us an overview in general of what on earth is going on in this solution. This is Crystal, and this is Matthew McGarvey's solution. And I presume this has been written just for fun. I don't think this is probably his idealized solution.
No, I think this is a very object-oriented like version. It's also a somewhat functional version, so it's quite weird. But it's actually like a whole rule set system. So so the rules are a set of functions that are being defined, and that those get executed later on. So there's a whole level of indirection. And I've seen a ton of systems that have something built into this, into their software, like a rules system, where the idea being that you code that once, and then it's very easy to have all these building blocks and you put them together. In this case, of course, it's total overhead. But I can see where, in some cases, the appeal of like a rule engine comes from, where you are just putting together different conditions and you can reuse them. You can reuse them anyways with functions, but many of those rule systems would allow maybe a graphical user interface where you can drag and drop things, etc. So I've seen it happen a lot too. And in general, this is just a lot of fun. So I don't think indeed that this is probably the most natural solution that people would think of, but it's still a fun solution, and it shows you that you can do very cool things with a static language like Crystal that still that feels dynamic.
Entirely. Well, if this code feels absolutely bizarre to you, then you can always jump into Crystal and explore this. But as Erik says, this is pretty functional. So you could try this out in different functional languages as well. So that was the last solution we wanted to look at. Hopefully that's given you a bit of an idea of how interesting such a simple exercise as Leap can be. If you went for the The basic JavaScript solution we looked at the beginning. Well, one, congratulations for writing some sensible code, but on the other hand, shame on you for not being more inventive. If you cheated, I hope this has given you some sort of incentive to try something a bit more complex. But yeah, Leap's one of those exercises that I remember the first time I saw it years and years ago, and I thought, this is a pretty boring exercise. But actually, you can do quite a lot with it. And when you move out of maybe the language you know best and start moving into some other languages, it's a really nice one just to start exploring and experimenting with.
And you can solve it on almost any track, because almost any track has Leap implemented. So
yeah, that's true. Yeah, it's pretty general across Exercism. Cool. This is, as I said at the beginning, the first one of these videos that we've put together. We're going to be doing lots more throughout the year. If you've got any comments on anything you would like to see in these videos, how we could improve them, based on the fact that Erik and I don't have too much time to either make or edit them, but what could we do in this hour that is fun, interesting? Please let us know in the comments. Really, really want to just make these as fun and useful and interesting and inspiring as they can be. Otherwise, please sign up to 48 and 24 if you're watching this at a time when that's still relevant. And yeah, I hope you have lots of fun with Leap. Erik, thank you for all of your finding the solutions and talking us through them and all of your insight in them. I look forward to seeing you all in the next video. Bye for now.